So let's start with rational tangles. We're going to define what rational tangles are, and then sort of begin to necessitate that all-important question about how do we untangle a rational tangle. If rational tangles have an algebraic structure, as we see that they do, then how does the invertibility property manifest itself? How do we untangle a tangle? And is it surprising that we should be able to untangle a tangle at all? I happen to think it's very surprising the first time that you think about it, and that's what this activity is kind of all about. So for starters, what are rational tangles? So a rational tangle is the result of taking two strands that we sort of fix at the four vertices of a square. And we start with what's called an empty tangle. I've got one sort of right here, if you can kind of see it. So it's these two strands are fixed at the top corners and bottom corners of my square frame. And an empty tangle is one in which they don't cross one another whatsoever. Right? So that's this empty tangle that we see up here. As you might expect, that's going to kind of serve as the function as the starting point, or almost like an identity element type tangle. So this is going to be how we know that we've untangled the tangles. If we can get another tangle back to here somehow, then we know that we have canceled out the tangle we're looking for. So it plays the role of the empty braid. In a way, we're going to think of tangles as being kind of braid-like, right? Because they have these two strands, and our goal is going to be to try to tangle these strands up in some ways. But there's only two strands. Unlike braids, where braids we can have a bunch of strands, and we use that number of strands to give us a lot of complexity in our structure. For tangles, we only have two, which, you know, certainly gives me a lot fewer things running around on my desk to keep track of. But it's not going to give us a lot of rich algebraic structure unless we decide what we can do to introduce crossings into our tangle. And unlike with braids, where every way to introduce a crossing into a braid involved twisting two pairs of adjacent parallel strands, in a rational tangle, we do have a twist, and we once again agree that a positive twist is going to be the only kind of twist we have, which is a twist of its own. The only kind of twist we have is a positive twist here, where the northeast to southwest goes down over the northwest to southeast gets placed above the northeast to southwest. What we're doing is we're taking those two strands and we're just trading those two endpoints in a way that sort of brings the top right corner strand over the bottom right corner strand. So to perform a twist, I'm just going to go over to my So if I want to introduce a twist into this tangle, I'm just going to take this top right corner and I'm just going to bring it down over the bottom right corner. So if I started from an empty tangle, then the result of doing a twist on that empty tangle is now I've introduced this crossing where my northwest to southeast is passing over my northeast to southwest. So this is the tangle then that we would call T. If I were to do that again, so bring this endpoint up and over, then I would get a tangle that I'm going to call TT, or T squared, if you like, right? And you can see T squared is a tangle now that has two crossings kind of here in the middle, and both of those crossings are positive crossings. So T is our first fundamental way of making a tangle more interesting, right? By adding twists that increase the number of crossings. But as you might expect, if that's all we can do, it's not going to be very interesting. It's going to be just like the braid group on two strands, which is not particularly exciting algebraically. And so we need some other operation. And the other operation that we have for rational tangles is a rotation operation. And in a rotation operation, as the name suggests, we take the entire tangle and we just rotate the entire tangle 90 degrees. We have to decide on an orientation for that. We're going to decide on a clockwise orientation. Actually, different authors that work on rational tangles use different conventions for that. We'll just agree for today, for us, that we'll use a clockwise rotation. So this tangle that we called T squared, if I then take it and I rotate it by 90 degrees clockwise, I get a new tangle that's called T squared R, right? So T squared R gives me the recipe for how to make this tangle. Add two twists in the ordinary fashion, and then take that result and rotate it 90 degrees clockwise. I could then, of course, keep going. If I wanted to add another twist, I could bring the top right down over the bottom right. And now things are starting to get interesting. Right? So this tangle would be T squared RT. I did two twists, then I did a rotation, then I did one more twist. And now I have a total of three crossings, if I zoom in on this middle here, And it looks like two of those crossings are kind of arranged vertically, and the third crossing is kind of arranged horizontally. And also, maybe the orientations of these crossings are not what we thought they were from before, right? So we can already see that rational tangles have the ability to get much more complex than we might have given them credit for, just for something that can have kind of two strands going for it. So this is t squared RT. This would be t squared RTR. I could twist one more time. Maybe I'll twist two more times just for fun. So this would be t squared RT. If I do it one more time, it'd be t squared RT. Be very careful every time we twist. Uh-oh. Something happened. I did t squared RT, and look what I have. I have an untangled tangle. So what's going on? That's kind of the question that we're asking ourselves for rational tangles, is that clearly these twists and rotations can act to make a rational tangle more interesting, intricate, complicated, but those same twists and rotations can also somehow make a tangle less complicated, to a degree that it can make it all the way untangled again, as we just saw. So figuring out what's going on here with the algebraic structure of rational tangles is our goal for this section. Rational tangles are also going to be an important source for us for where we're going to get knots from in later sections. Although unlike braids, not every knot that we can tie is going to arise as a rational tangle in the beginning. A lot of them do, but not all of them do. Unlike braids, we can actually show that every knot has a braid that underlies it, but not every knot has a rational tangle that underlies it. Many of them do. Those are called the rational knots, but there are some that don't. And so rational tangles, while they have a great structure, they're not going to tell us everything that we could ever want to know about knots, unfortunately, which is one of the reasons that knots are so widely studied still, and there's a lot of open problems still in knot theory and mathematics, because rational tangles, it turns out, are fairly easy to get our hands around once we learn enough facts about them. But knots are still the gift that keeps on giving.